Actually, let's be real. I'm not getting very many people participating in these videos, but we should. The numbers are getting high. So, I mean, it's obvious just in this class alone. Anyway, here we go. The quiz. So if you're a quarantine kid, pause the video that you're watching and take that quiz in Canvas. It's located in the Concentrate on This Part 1 module towards the bottom. Okay. Pause that, do that. Now the rest of us that just took it, here is our data, which isn't bad, but it's not great, but that's fine. We learned this yesterday. Let's make sure we are good. Every single one of these questions will be on your exam. Every one of them you'll see again. We okay with that? Good. 77%. I'm really not going to complain about that. This is not a trick question, but it can be tricky to answer. If 3 graduated cylinders are filled with water, one contains hot, one contains cold, and one contains room temperature water, which one will have the most? This is really a question that's saying, which is the more dense, the hot, medium, or cold? You could answer that, couldn't you? Which one's more dense? The cold one. So please, please, please remember the number of particles in a given volume is the same as saying density. So it is the one with cold water. All right, which graduated cylinder has the lowest density? As temperature increases, the density decreases. So good on that one. Which one has the fastest moving particles? Please, if you got this wrong, write a note to yourself. Temperature is measuring the speed of particles. The hotter, the faster. And which graduated cylinder has a density between? Don't get this wrong. Medium. Remember, liquid is the medium one. So I know that we had gas and solid, and these are all liquids, but the one with the medium temperature water, that will be the one that is between the two. So overall, not too bad. Okay, coming down here. So this is the table on the top of page 3. So I mean, we're at 92. I won't go over all these. Well, I better go over that one. A relatively low temperature. You need to remember solids are the low temperature. If you would think about the following, when we think about a solid, a liquid, and a gas, think about it relative to something you're familiar with. Treat the solid as though it's ice, the gas as though it's steam, and the liquid as in just liquid water. The ice is the cold one, the steam is the hot one, the liquid is the medium one. Okay, just think it all about water. You're familiar with those. Whoops. Oh, where am I going? Oh yeah, I needed back to the internet. Let's hope it's that right there. Nope. Oh, hey, well, whatever I did, it worked. Okay, so a relatively low temperature needs to be the solid. Looks like some of you didn't get this question, which is fine. A high number of particles. Please, please, please. Density and number of particles are the same, so that would be the solid. A solid is definitely more dense. Like if I were to punch this, it would break my hand because this is a solid. But I can punch the air all I want. I'll just look really odd. All right, low number, that would be a gas. That's interesting. Why would we get these wrong? Like you would assume that it'd be 92% on both. Medium. A medium is always a liquid. Don't even think, just click it. Low density is your gas. Large space is your gas. Medium speed of particle. Oh yeah, there we go. All these people. Let's celebrate these 13 people. Now, if you're not on that list, it doesn't mean you're dumb. It means you didn't get this question. So anyway, congratulations to all of those amazing people, even Pearson, who can't spell his name. I don't know. I just like to pick on you. I don't think I've ever spelled it right when I've had to like type it to Rollins or something about track. All right, next, which is not part, oh, this is no bueno, which is not part of the kinetic theory of matter. One of these is just a plain out lie, and that would be the speed of particle decreases as temperature increases. This is an incorrect statement, which means it is the correct answer, but it's not part. Okay? Maybe I should make that bigger, bolder, and more capped. All right. As the temperature of a substance increases, the density of the substance will decrease as well. Okay, not bad. You'll see all of those again. That's the first quiz, essentially, on the exam for competency number 1. Fair enough? And you can retake this as many times as you feel like so that you see every single part of it. Okay, next, heating curve for water, page number 3. Will you all turn there? You guys are such a quiet, obedient class. I appreciate that. All right. So this is also something that is on your exam. And if I remember right, I have a short little video I just remembered of this. All right. I swear I've recorded this 20 times, but I don't know where I've put it. Fine, we'll go to our good old friend YouTube. Okay, this looks like it will be amazing. 4 minutes and 16 seconds of watching this graph. Who is super hyped? Okay, now I watch everything in double speed, so you're welcome. We'll only do this for 2 minutes. Whoops, that's the wrong one. Come on. If I could give you advice in your life, it is learn how to do everything at 2 times speed. My Audible bucks, I'm up to 2.4 speed, and it saves me so much time. And another book I read a lot. I can blow through those. Okay. So what is happening in this video is this guy, wow, heat is being added, but the temperature is not changing. So you have ice water that's being stirred, and that hot plate is heating it. This graph is showing you the temperature versus time. Now notice that the ice is starting to disappear, and tell your partner what's happening to that line as the ice has started to disappear. What's happening to the temperature? It is increasing. Thank you. We don't need this audio. Sounds like my computer's breaking. Okay, now we have the line that's now going pretty quickly up. All right, so you can see right here, they're flying by. Halfway there, it's still being heated. The line is still going up. I like that. I have one of these heated spinners, I think. Maybe I should try that. He's giving away all the answers, is the sad part right here. Okay, we're getting close to 100. What's going to start to happen at 100? It's going to start to boil. All right, it will be hard to see. Now I just got really emotional right there. All right, he stopped the spinner. That's good, because it would have been hard to see that it was boiling. Okay, now let's look at this graph. I don't know how far this goes. I've never used this video. All right, this person must live at a lower elevation than we do. Anyone know why I know that? There you go. Because here in this room, it usually boils at 97 point something. Okay, so this is the shape that we're looking for. And I'll go forward to a slide to make it look a little better. But it stays flat. What is wrong with me? I need more fuel. Hold on. All right, it stays flat. Now, I'm going to ask you to talk to your partner. And I love that you're a quiet class, but sometimes talk a little bit more. I want you to tell your partner what was in the beaker when that line was flat. Ready? I have the keys to the closet. Now, I lost my keys not long ago, so please bring it right back to my hand. Burgraff, do you see the shirt? It's hard. This is the one that's really hard to tell, but I promise you it's a Burgraff shirt. Okay. Has anyone noticed I've worn a Burgraff shirt every day this week? Besides Sophie. Yeah, well, fine. You better. All right. Did you tell your partner? Ready, go. What's happening when the line is flat right here? What's in the beaker? Any ideas over here? Ice and water, right? Okay, ice and water. Now, let's restate that with phases of matter. In the beaker right here, I had some solid and some liquid. Okay, so let's think about this. I'm adding heat to the solution, but the temperature is not rising. That doesn't make any sense, right? Heat is energy. Will you and your partner have a short discussion then? Where is that energy going if the temperature is not rising? Ready, set, go. I'll pretend you're on time. Oh boy. Any ideas? Am I smart? That sounds mean to everyone. All right. Anybody have ideas? Go ahead. Okay, the energy is going towards the solid. That's a good answer. What is happening is the energy is being used to make the state of matter change. It requires energy to go through a phase change. So that line is flat because it requires energy to break the ice apart. Now, once there was no more ice, then the temperature goes up. That's because all of the heat is now going into the water molecules to speed them up. Now, at the top, it goes flat. Even though you are adding heat, why is the top flat now? Can you tell your partner now we have an idea? All right, I heard a couple of people say it's because of phase change. That's dead on what we're looking for. It's because of phase change. Now, I would like to talk about how this line right here has caused one of the bigger fights in my marriage. Okay? Now, just to start off with this story, I didn't win this argument, and I never will, even though I'm right. So, I love my wife enough that we'll just work through it. So here we go. Years ago, well, it's been for many years, my wife and I get in a fight about this because I will make spaghetti or mac and cheese or whatever, and I have the burner on high until it starts to boil, and then I turn it low. And in my life of being an adult, I can only remember one time that I let the water boil over the top. One solitary time, and that's because I was at the door talking to someone else. One time. Now, I love my wife, but I can think of probably 100,000 times that the water is boiled over when my wife could. Because to me, she doesn't understand science. Union High School Science Department. When you bring that water to a boil, do you need the heat on high still? No, because the water stays as hot as possible until all the water's gone. So just turn it down. As long as you're getting 1 or 2 bubbles, you're fine. And so one time, as a male, and it was a dumb idea, I took all the equipment that I have home here to show my wife when I cook noodles, no matter how high the burner was on, the temperature of the water was the same. I had a graph, I had it all perfect. I stated my case to her honor, and I said, look, whether it boils over or it just barely simmers, it's the same temperature. I win. Will you finally accept that? And then she said, no, the bubbles must make it cook faster. And that was checkmate. I don't have any scientific tool that I can prove to her that the bubbles have nothing to do with how fast your noodles cook. So I lost. I've been a loser my whole life ever since. So, boys, there's a lesson there. Just let your wife win even though you know you're right. There's lesson number 12 from this class. Did she bring my key back? I'm going to kill him. Derek, where's my key? Are you uncomfortable with that? Is it weird that I find Derek's mom to be attractive? Sorry, that was awkward. Yeah, that's right.
I was gonna not return it and be funny, but I'm scared that I'll actually forget.
Yeah, and you would be in trouble. All right. Goodbye, my friends. Oh, I am always happy. Okay. What? Am I not? I did. This is a sad thing. Why am I wasting time? Sorry, online kids, but there's no one there. I'm teaching no one. With some church stuff, I was in a meeting and then I went to a different thing, and someone in that meeting, well, not meeting, we gave someone an assignment and then they just didn't do it. And they basically made up all these excuses. And inside me, the rage monster was going crazy. Okay? I was like, okay, I guess I'll do everything. Yada, yada, yada. Long story short, I was mad. Then yesterday, I'm in a meeting again with the other people that were also there except for that person. And I said, did my face look as mad as I was? And this guy's like, you always look mad. It doesn't matter. I was like, oh, busted. Sorry, I guess I don't have to pretend to be happy then because it's pointless. All right, moving on. The good news for you is I have a mask, so you don't know what I'm looking at or looking like. Okay, whoa, there it is. Let me erase all this, then we'll redraw. So what I want, oh, it's already there. So the curve is here. Now this one's a little bit different. It starts down here. From whatever temperature I want up to 0, this is for water, it's a solid. Now the line is representing the temperature versus how much heat I add. Okay, so from here, and it should already be labeled, this is your solid. As I add heat, the solid just warms. Okay, we would never think about it, but you get ice out of your freezer, that's pretty cold. Before it melts, you got to heat the ice a little bit. Then once it gets to 0, it will melt. All right? Now, we have labels when we're warming, and we're going to have labels when we're cooling. All right, so when we go from a solid to a liquid, we're melting. When we go from a liquid to a solid, we're freezing. This part right here is called the melting point, but this could also be described as the what? Freezing point. I would label both. It just depends if you're going from cold to hot or hot to cold. All right, now, and remember, this line is flat right here. That's a terrible arrow, but that is flat right there because of phase change. You don't have to label that on a graph, but you have to be able to explain why the lines are flat at 0 and 100. And the explanation is the energy is going into phase change. Okay, once we're in just one phase, like liquid again, all the energy is just raising the temperature. Then when a liquid gets to 100 degrees, so we're moving from cold to hot, we call that boiling or the boiling point. If we go from a gas to a liquid, we call it condensation. And you don't have to call this the boiling / condensation point. We don't talk much about condensation. But now, look right here. This line is flat. Why is this line flat? Because of phase change. Will you look at these two flat lines and notice something? That was probably a terrible color to choose, whatever, but we can still do what I want. Okay, so I'm going to bring this one here and this one here. Will you compare those two lines in your mind and think, what? Draw some sort of conclusion in your brain to explain why this line is so much shorter than that line. We can make an inference here. We can come up with the idea. Why is one line so much longer than the other? Have a think about it, maybe talk about it for a second. Ready, set, go. So much silence. Okay. Those of you that talked, I appreciate it. It is kind of a confusing question, so I'll give you that. And you probably think I look ornery, so you're scared. But here is the answer. It takes way more energy to convert a liquid to a gas than it does a solid to a liquid. And if we think about that picture I drew yesterday, like this is showing you a gas, right? And then liquid, and then solid. Here's what happens. A liquid, the particles are still really close together, right? They're not as close, but they're still close together and they are attracted to each other. If they weren't, water would just fly away, okay? So water is definitely attracted to each other. That's why it comes out in a stream, all right? So it takes some energy to break all these little bonds between each particle, but it takes a ton of energy to go from a liquid to a gas because every single attractive force between the water molecules has to be broken in order for something to leave as a gas. So that takes way more energy than it does to just loosely arrange them instead of completely unarrange them. Okay, now, on the exam, you'll have this exact picture, and it's just labeled with letters. So it'd be like A, B, C, D, E, F, G, H, I. Now that lettering was dumb because I went out of order. But you have to match every letter to every part. So it's not that hard. The only thing is you need to remember if it's the arrow, it's the process. So if you're looking at D, that's melting because that's the arrow from solid to liquid. If it's just the thing that says like over here without an arrow, that would be melting point. And the way it's on the test, I think I've made it super clear. Kids have been scoring really high on it the last 2 years. Okay, thumbs up, are we okay with that? All right, I took more time. I think I answered them at the bottom. Define what happens on a particle level as a substance changes from a liquid to a gas. That was this conversation a second ago. All attractive forces between molecules are broken. All attractive forces between molecules is broken. A good analogy of this, by the way, like, well, I'll let you write that and then I'll just say something real fast. Okay, so stick with me for a second. Who's gone to an assembly in the auditorium at Box Elder High School? Okay, so look, this is you while you're sitting in your chair. We'll say that's the representation of a solid. Then when it's over, this is when everyone stands up. And that took like a little bit of energy and a little bit of time. This is after every single person's left the auditorium. Which one's easier, to stand up or get 1,000 kids out of the auditorium? Stand up. It doesn't take that much energy to go here. To disorganize everything or everyone leave, it takes way more. Okay, number 2, the buggy that I always read over your shoulder. Why does the temperature of boiling water remain 100 degrees until all the water has been changed to steam? Remember, temperature measures the average kinetic energy. All right, here's the real answer. I guess I didn't say it. I was too busy talking about my fight. So here is your pot on the stove. All right, and here's your water. Any particle that is over 100 degrees, do you know where it's going to go? Oh, no. Okay, well, they're all going to be up there. It's going to leave, right? So it stays at 100 because anything above that point leaves the liquid and becomes a gas. So if we're just measuring the temperature of the liquid, it will never get higher. Oh my goodness. So let's think about this, and I'm not being mean, but every test, if I took out everyone that got an A, and they were like, all right, leave, we would get dumber as a class, wouldn't we? Because the only thing left would be the ones that didn't get an A. All right, now eventually, I'd get down to 1 or 2 kids, and my kid, man, if I had all day to teach just 2 people, you would all get A's, I promise. And then they'd all be gone, all right? That would be like boiling all the water. But if anything above a certain point leaves, then what's left will never be above that certain point. Okay. I just heard mumbles, sorry.
Everything has to get to 100 degrees.
Yep, to evaporate it all, everything would. Okay, go ahead and try and summarize that. Much better picture. Yes, ma'am. Okay, hold on. Yes, question. All right. The next thing we're going to do, if you would turn to page 4, you will see a bunch of experimental design boxes. Oh, you thought you were done. The answer is never. All right, so let me cut and paste some and we can talk about this. All right, we have in chemistry, there's a few things the state requires, and one of them is literally this lab. They require that students design and conduct an experiment to test the factors that are involved. Shoot, I had it word for word. To study the factors that increase the rate of dissolution. So, give me a second. I should have this open, but I was, let's see, that one. Okay. It's coming. So on Monday, is spring break just Thursday, Friday, or is it Wednesday, Thursday, Friday? Well, that's a letdown. What did I say? Oh, eat it, people. You know what I mean. Sorry, that didn't sound very kind. I'm not going to make it as a kind person. People don't know what to do when I'm nice. Like, what is he trying to prove? Okay, so here we go. Problem: to devise and conduct experiments that demonstrate how the rate of dissolution can be changed. So we better make sure that we know what I mean by a rate of dissolution. So the rate of dissolution is how fast something dissolves. How fast something dissolves. Now, I'm going to turn the time over to you in just a second. So hopefully this goes all right. All right, so instructions: construct, and I already printed one. Instruct an experimental design box to test the effect each of the factors listed below has on how fast something dissolves. In each experiment, the dependent variable will be the time it takes a substance to dissolve. Also, make a numbered list of the procedures you will use to conduct the experiment. After performing the experiment, record your results and make a conclusion. So we are going to test 3 different things. Particle size. In order to test how particle size affects the rate of dissolution, I am giving you rock salt, which are like large particles, and table salt, which is not large particles. You and your lab partners, you are going to fill this in, come up with some procedures, and then you're going to take some results, and then you're going to make a conclusion graph that looks something like that. Okay? Okay, that's not a function because it's not roller coaster safe. Do they still teach math that way? What? Yeah, when I learned math, you knew if it was a function, if it was not roller coaster safe. It could, if it went like this, that could be a function. Whoops, that wouldn't be. Moving on, I'll shut up. Okay, So come up with your problem. Your problem is roughly like, how does that affect the rate of dissolution? Your IV, your hypothesis, all that. Now you're going to do it 3 times. I didn't cut the other ones, but this one's particle size. The next one is agitation or shaking. So in that one, you're going to shake or agitate some and not others and see how fast they dissolve. And the third one is temperature. You'll use hot water, medium water, cold water, or whatever, and test them. So what you have now for the next 10 minutes, work with your partner and fill out these design boxes and come up with procedures. I have beakers, test tubes, pipette, graduated cylinders. I'll have hot water, I'll have rock salt, I'll have table salt, I'll have like stirring things if you want. You can cork them and shake them, whatever you want. You come up with ways to conduct this actual experiment. This is going to require you to work with your partners. Ready, set, go. No, you're not doing the experiment now. You're filling in the tables and writing the procedures. You'll do the experiment on Monday. My fault. Okay, onliners, you can actually still do this at home even though you're not here. So, we will have more time to set these up on Monday, but remember a few things about design boxes. Typically, you can find your IV and DV in the problem when you set those up. So the particle size, and then your problem is how does particle size affect dissolution? Perfect, by the way. Then it tells you your IV is particle size. It tells you your DV must be the rate of dissolution. Then it tells you you'll have table and rock salt. So those are your 2 treatments. You're going to do 2 trials, so put a 2 under both of those, and then we'd be ready to go. Agitation, temperature, pretty much the same type of box, just a different independent variable and treatment. Okay, Monday, we'll have a little more time, and then we'll do this lab where you literally get to stand there and watch salt dissolve. It's fascinating.